Look up long enough on a clear, dark night, and you will be able to see a bright band of stars rising and setting with the others. This is the plane of the Milky Way Galaxy, seen from our location out on one of its spiral arms, slightly above the galactic disk. It is our continent in space, filled with a few 100 billion stars. Look elsewhere in that same night sky, and we find that for every star in the Milky Way, there are around 10 galaxies in the observable universe, about 2 trillion of them, and that they are clustered and spun by gravity into nerve-like tendrils called galactic filaments. Some of these distant galaxies are disks, much like our Milky Way. But the closer we look, the more differences we notice, from the hazy shape of gargantuan elliptical galaxies to the widely varying amount of metal in a galaxy's stars. Why are there so many galaxies, and why are they arranged this way? In the wake of the Big Bang, tiny variations in background heat left over from early quantum fluctuations molds the homogeneous expanse of superheated matter into areas of higher and lower density. Dark matter amplifies the strength of gravity, drawing visible matter into thick, whirlpooling tendrils of cooling gas and sculpting the biggest things we know, the galactic filaments and voids of empty space. As small structures like stars form, so do larger, composite structures like galaxies. Gravity and angular momentum work in tandem to flatten a rotating cloud of infalling, diffuse matter into a disk, much like a tossed pizza. The most stable place for matter to be, flung outward by rotational energy, but also tugged inward by gravity, is in a disk perpendicular to the galaxy's axis of rotation. We think disk-shaped galaxies are younger, they typically have brighter, bluer stars. Their quickly rotating disk is interrupted only by a local bulge of stars in the center dominated by the mass of a supermassive black hole. Occasionally, stars that venture too close to it are ripped apart by the intense gravity and smeared into an accretion disk, and as the black hole devours matter, it can accelerate jets of particles out into space. These jets create temporary bubbles and plumes along the galaxy's axis of rotation. In far-off galaxies, we see these jets at quasars. In our own galaxy, we see evidence of past violence in 2 Fermi-bubbles. Around the disks of young galaxies stretch spherical halos of dark matter and gas. Observations of colliding galaxies tell us that these halos are much larger than the luminous galaxies themselves. Galactic mergers, aside from sparking new flurries of star formation as gas fields collide, can create an entirely new kind of galaxy. Elliptical galaxies might look homely, but don't let their nondescript appearance fool you. These are some of the most developed and complex structures in the universe. We think they form when younger disk galaxy mergers that send stars off in wild orbits outside original galactic planes. Within a few billion years, the Milky Way and Andromeda will merge and form such an elliptical galaxy, and as it cycles through new generations of stars, Milkdromeda will gradually grow richer in metals and heavier elements and poorer in free gas and dust to build new stars. Just about everything we know about galaxies comes from comparing our distant observations and our understanding of physics with different models and theories. Each new, more detailed observation we make allows us to find new discrepancies in our models and refine our understanding of how matter works at the largest of scales.